everybody. Thank you for inviting me here. This talk is in English, so sorry for my English because it is at the same level of our Prime Minister, so good luck with me. And before starting, I just introduce you about myself. I started as an electronic engineer some years ago, and then I moved to research, and I took my PhD in computer science at the University of Bologna, where I developed a formal theory for service-oriented computing and a service model that later we transformed into a programming language that is called Jolie, and then that is one of the main topic of this talk, so I will discuss Jolie later. Then, starting from this new technology, we also started up a company some years ago, and then this company now is part of the Imula group, that is a consultancy group, and then we are more than 100 people employed in the Imula group, so Italiana Software now is in this group. And we are based in Imola, where some years ago we had Formula 1 Grand Prix, this place. So, but a linguistic approach to microservices is the title of this talk. That seems interesting, but why, or what does it mean, this kind of title? Before starting to introduce it, I would like to start by showing you a little discussion about how the nature of computational resource is going to change. So far, in our mind, we are usually think to the computer resource as a single computer on our desktop. Okay, but as everybody of you know, we are moving to a computational resource that can be seen as a distributed network of computational resource. So, what does it mean? The single computer is naturally not distributed. Okay, and the processes are focused on computation because we want to program the computation of the single machine. And so, programming language deal with functions, procedures, and objects. But the new computational resource is naturally distributed, okay? And more of the processes are focused on communication and orchestration instead of computation. This doesn't mean that computation is not important, but are emerging the new features like communication and orchestration. So the new words now are services, microservices, nanoservices, and so on. Okay. Another important thing is that this computational resource is evolving, starting from the real single machine towards containers. Okay, we are finishing the virtualization era, and then we're approaching the containerization one. Okay, so we can see our computational resource on different layers of abstraction, where on the bottom one we have the real machines, and on the top we have containers. Okay, so but now everybody can reach also this layer, can manage this, but we are thinking that in the next future maybe nobody will see this layer and everybody just can see only the top one, the container layer. Okay, so for us the new machine is a machine built with a lot of containers, hundreds of separate components that must communicate together. Okay, so what does it imply? We believe that all the procedures we have to adopt for developing application inside this new machine will change. And application will be more close to the composition of existing containers inside the machine. Okay? So, another important element here is that the abstraction of a container is more close to the software functionalities it contains, and then with respect to the virtual machine. And the virtual machine, we keep the idea of the single machine, but it is virtual. In the container, we lose the idea of a virtual machine because we have just a container which contains a software functionality. So for us, in the abstraction layer of the computer machine, we have software functionalities that are separate components that can work together. Okay? So this is why, for us, communication and orchestration are more important than computation. Because computation is limited inside each single component. But the value will be in how we are able to integrate, to make communication and orchestration among these different elements. Okay, I think that everybody knows containers, so I can skip this slide about containers, but if we focus on how we program containers, everybody knows that we program an image, and then from the image we instantiate the container. So, what we are programming when we are programming a container? We program the application, and then we program the installation script for creating the container image. Okay. So, the novelty with container in programming container is containerization, the installation script programming language. But what is old now? The applications are programmed in the same way that are programmed 10 years ago, 5 years ago. Nobody changed for the application inside the container. We just changed the what is on the edge of it. Okay? So the question now is, what is programming in this new computational resource that is made by a lot of hundreds of containers? So now we are focusing on this step. Okay, how we can revolutionize this step. Okay, from our point of view, we can program programming this kind of elements can be seen in two different aspects: single component programming and architectural programming. Okay, single component programming deals with what we are putting inside a container. And architectural programming means how we create the right communication among them. Okay? So, let us now to analyze how single component programming works now. I think that from all the experience you have, and then also from the keynote we listened so far, programming application means using a couple of elements, libraries and frameworks, and then a programming language. Okay? If you use Java, you can use Python, you can use what you want. But together with the programming language, you're using a lot of different libraries. Okay? And usually the libraries deal with the communication and orchestration aspects, because the programming language are focused on computation. So if you want to enrich the technology you have with the functionalities for communication and orchestration, you need to add external libraries for doing this, or external tools. Okay? So, libraries together with programming language gives you the right technologies for programming inside the container. But the programming language are more stable over the years because the syntax changes slowly. On the contrary, libraries are very dynamic. We have new tools every day, new versions. We have continuously to learn how they work and how we can use them inside our projects. Okay? So, our knowledge, our time, is absorbed by the libraries, not by the languages. Programming languages need few weeks of training, and then we are able to program with this kind of language, but our time is devoted to learn and use libraries, okay? So our knowledge is absorbed by libraries and frameworks. But knowledge is money. So the main part of our business is absorbed by the management of this kind of libraries and tools instead of the programming languages, okay? So our idea is, why don't we move our knowledge from the libraries to a new programming language that is able to free our time, okay? And this is the programming language that I introduced at the beginning of this talk, that is called Jolie, okay? So our aim, our final aim is to produce a new programming language that is able to reduce, not to cancel, of course, to reduce the knowledge we put inside libraries and frameworks. Jolie, you can find Jolie and all the information about this programming language and the website www.jolielang.org. If you just put Jolie in Google, you will find a lot of Angelina Jolie images. So just put Jolie and programming language so you can find it easily. Jolie was, as I introduced you before, Jolie was born from a theoretical analysis about service-oriented architectures. Starting from all the specifications in this area, we distilled process calculus that is called SOCT with the formal operational semantics. And starting from this formal model, we developed Jolie. Jolie has been developed in Java, so it needs a Java virtual machine for working, and then it is interpreted. So you write your script in a simple text document, and then you run the interpreter that is interpreting the script you wrote. So it is not compiled. The engine is developed in Java, and everything we are doing with Jolie is a service or a microservice, if you want to call it in this way. So, in our perspective, in Jolie, a service is a single unit of programmable software, which means that you cannot program something different from a service. You can only program services. As in Java, you can only program classes, okay? In Jolie, you can only program services. There are no trade-off on this. Everything you do is a service, okay? I would like to introduce some basic characteristics of this programming language in order to give you the basic ideas on how we try to reduce the libraries, as I told you so far. Jolie is communication-centered. So for us, it's very important to define the endpoints which are collaborating each other inside a system, distributed system. So in Jolie, everything is distributed naturally. You cannot write something that is not distributed, okay? You can deploy it as a monolith if you want, but even if it is a monolith, it is distributed inside, okay? So the definition of the endpoints, communication endpoints, is very important inside Jolie. And we have two very simple constructs that are called output port and input port. Okay, you can see here. What does they mean? First of all, they define where I'm sending a message and where I'm receiving a message. So if I'm defining an input port, I'm defining where I'm receiving. If I'm defining an output port, I'm specifying where I'm sending the message. And the location just specifies where the endpoint is listening for. It is composed by the medium, that is socket, usually use socket for communication, and then the IP, the address, and the port where we are listening. And on the other side, I just specify the same address because I want to communicate with that specific endpoint. Then we specify how we create the communication. So we specify the protocol. SODEP is a custom Jolie protocol. We use SODEP when we want to make communication between two Jolie microservices. But here you can also specify HTTP, HTTPS, and so on, because you are able also to communicate with other services that use different protocols, SOAP and so on. Okay. Finally, you define what the interface is. That means what are you exposing to the others in order to be called back. Okay? You can see interfaces like a sort of Swagger definition of your API, or something like similar to a WSDL if you are considering web services. Okay, it's the same. Okay, nothing changed. The most important fact is that the definition of the interface is defined inside of the language. It does not come from an external technology, an external tool. It is inside of the language. Okay. Another important fact is that inside the same microservice, you can define more than one port. So you can have more input ports which are listening on different protocols, for example, or you can have more output ports because you can have dependencies with other microservices, more than one microservice, of course. Okay. The language definition for the interfaces is very simple, because you have a keyword called interface, the name of the interface, and then you have two kinds of operation you can define, the request response and the one-way. Request response is a synchronous communication. So you send a message and then you are waiting for its response. Okay, so you are waiting for the response. The one-way is the asynchronous one. I just send the message and then I can continue to work. Okay? And then we can define the types of the message that are tree-structured types. So very similar to JSON or XML tree structure. Usually all the variables have a tree structure. So how we can program a communication inside the behavior of a microservice written in Jolie. So in Jolie, you can find a scope that is called main, that contains the main behavior of the microservice. And if I want to send, for example, an asynchronous communication to another microservice, I just write this: the name of the operation, the name of the output port I want to use for sending the message. The output port is here. And then the variable that contains the message. This variable can be read with request.field, means that this variable contains a subnode that is called field. And this subnode contains a string that is called hello world. So when the interpreter executes this, a message starts to this output port that is delivered to this input port here. And here, the behavior is listening for a message here in an operation that is the same name, of course. Here the message is stored inside of the variable on the receiver, and then you can use it for continue your behavior. The synchronous is very similar, the synchronous call, because here we are sending a message on a request response operation. Okay, I send the same message, but here I'm waiting for the response. So the sender is blocked here, waiting for the response from the receiver. As you can see, the receiver defines the request response as an atomic action. So he receives the message of the request, it executes the body, so you can do something with this kind of variable, and then you prepare the response variable. At the end of the scope, a message will send back to the invoker. Okay. Another interesting aspect of Jolie is how we manage the behavior of the microservice. And since everything started inspired from WS Beeple, I don't know if someone of you knows this kind of technology used usually in big service-oriented architecture for creating orchestrators. It's a very, very difficult and complicated technology that exploits a lot of tools for managing this kind of orchestrators. But we extract from this technology, I think, a very good aspect. That is the workflow approach. So everything you program inside Jolie microservice is a workflow. That means that you can also program part of sequential definition of activities that is very common. Also the parallel one. That is very simple because if you just use the pipe, it means you are parallelizing these two calls. Okay? And the parallel is finished when all the activities inside are finished. Okay? So if we write this kind of behavior, it means that I'm receiving a message here. I'm executing two calls concurrently on two dependencies, and when both of them are finished, I can send back the message to the evoker. Okay? And then clearly the language has a lot of features with respect to this. I just, since there is no time for introducing you to all the language, I can just give you the core primitives. But there are a lot of other primitives also for managing faults and so on. So I started saying a linguistic approach to microservice. I think we are doing this. We are creating a new programming language that give you the possibility to natively program microservices. And apart from the features it has, I think the main primitives we have with respect to the other are ports, interfaces, communication primitives, and workflow behavior. So the language is focused and is centered on this. Okay. So, how we can replace the old and traditional technologies with new one? Jolie can be used for programming inside the container. Okay, for changing the way we are thinking to the microservices inside. So we have the possibility to simplify the development chain of what is inside the container. That is more close to the nature of the computational research we have. Okay? Programming architecture, I just give you a very brief idea of what we have here. So, if you know containers, you can easily know that a containers, you have to bind containers together if you want that they communicate. So you need to create the binding. You can move them very easily, and then you can scale them. Okay. In Jolie, we don't care about this because there exists already some kind of tools for doing this kind of this. But what we are doing, we are trying to introduce primitives for programming architectures. Okay. So for us, if a service is the single unity of programmable software, a composition of services can be always considered as a service. I think this is a very powerful statement, okay? Because all the primitives I will show you now in a very quick way, they always produce a service, okay? So everything we are dealing with are services or a composition of services that can be seen as a service, okay? So what are these kind of primitives? The first is a very simple primitive that is called Redirection. Yes, thank you very much. And we receive a message on a master microservice, and depending on the resource, we are able to redirect the message to the right target. Okay, it's very simple, it's a proxy. Okay, but how we do this in the language is very simple because it is wrong because subservice and subservice should be called A and B. I didn't correct them. So you have two output ports, A and B, or subservice or subservice, and then you have the input port of the master, which receives the message. With this primitive redirects, I'm saying that if you specify the resource A in the URL, your message will be redirected to the target output port, A or B. Okay. We have also aggregation that is very similar to redirection. It works similarly, but here the invoker, he does not see what is hidden by this master service, because here the aggregation primitive aggregates all the operations of the back-end microservices here. So here I just see one microservice with all these operations. Okay. At the same as we did before, here instead of redirects, I just specify the name of the output port, A and B. So when M receives a message, it is immediately redirected to the service that are implementing that operation. Okay, and if you have different protocols, so or HTTP, for example, it converts the message. It does not work every time, because sometimes HTTP, this kind of protocol like SOAP or HTTP requires specific customization, but it has a good result. Then we have Courier. Courier is a new primitive for doing something before delivering the message to the target. So here I can define in the master Courier scope, and then before sending the message to the target, I can do something else. For example, calling other service. I want to check the credential, I want to log some kind of stuff. I can do this before forwarding the message. I have just a minute. Then collection is very similar to Courier, but I can have a collection of identical microservice that implements the same interface, and depending on the data on the receiving master microservice, I can deliver. For example, you can have microservices that collect all the address of citizens in different cities. For example, the first one could deal with all the address of Rome, and then the second of Milan, and then the second of Bologna, I don't know. And if all of them have the same interface, if in this message I specify Rome or Milano or Bologna, immediately it is automatically redirected to the right target. The last one is the embedding. That is very important for me. I can specify that the master, when it is executed, inside it executes also other microservices. In this way, I'm able to use less Java virtual machine for more microservices, because everything is naturally distributed. So theoretically, I should have a Java virtual machine for every microservice. But in some cases, it is not so important to have a different Java virtual machine, because some microservices could just provide very simple functionalities, and I don't want to distribute them, because in that moment I don't care about this. So I can specify that the master service can embed the children microservices inside the same virtual machine. So I can optimize the usage of virtual machines inside my machine. This is why I said you before that I'm programming distributed, but I can deploy also a monolith, because I can build a monolith in a distributed way. And in every moment, I can decide just to take this, change the location, put it in another machine, and everything is the same. So the first design of the architecture does not change depending on where I'm putting the different microservices. Okay? So at the end, what we want to do is thinking in microservices, thinking and programming in microservices. So in our idea, when a developer is thinking to a microservice, he should have an immediate and concrete representation in a programming language of his ideas. Okay? And what is important here is that every relationship with every entities in the mind of the developer as a correspondence with a dependency, a real dependencies among microservices in the architecture. Okay? And moreover, if I want to fragment the functionalities inside a microservice, because I have a microservice that is too big, I want to fragment it, I can create other sub-microservices that will be deployed inside the same virtual machine. And then if in one day this sub-functionality will be promoted to be a microservices for used by everybody, I can just take it and put it outside. Okay? I have 5 minutes, right? Less. Okay. So the main idea is that thanks to Jolie, we can jump to a new era where programming language naturally provides microservice programming paradigm. Okay, where everything you think is a service, and then you have the mean for producing it. Okay. Since everybody is using Docker, we also developed Jocker, that is a project where we wrap all the API, HTTP API of Docker in order to control a Docker with an orchestrator developed in Jolie. So, thanks to Jocker, they are just the initial step, so we are working on it. They are not completely done, but they are working for the basic features. So we can control a Docker infrastructure by orchestrating them with a Jolie orchestrator. So we do this in the case of development because we are able to extract the code from a Git repo and then put a Jolie microservice inside a container and then create an environment. Okay, I'm finished. But it's 32 minutes. I have 3 minutes more. Just for me. And so just for showing you that we use this kind of technology for creating an automation of testing of all the microservices we have. And then we also have a nice experiment where we can transparently change asynchronous communication into an asynchronous one and then vice versa. Okay, but I have no time for explaining this. We clearly, it is not Jolie alone, but we can integrate it with other technologies. No, there is no problem. You can use all the Java code you have. You can wrap it inside Jolie if you want. No problem. And then we exploit Jolie also in industry, like thanks to Italiano software, we developed a suite for just controlling and showing the microservices you have in your environment, and then you can control stop and start them and deploy them. You don't need Jung for making your architecture working. That it is just a facility you have just for seeing what is happening on your system, and then we commercialize this kind of product. And the nice feature of Jung, it is that inside he has a component, specific component for integrating it with SAP. So we have a lot of customers that build their integration flows thanks to Jolie and JSON, because it is very simple. Okay, I'm finishing my presentation. 33 minutes, so 2 minutes less than. And if you have questions for me, yeah. Okay, thank you very much.